Thank you for coming to my talk. My name's Matthew Arnott. I work for OFR Consultants. I have done for the past 4 years now, and I've recently started specialising in evacuation modelling. So today's talk is on counterflow and computational evacuation modelling. We look briefly at the hydraulic model, modelling tools, and some trials that were undertaken in the company. Co-authors on this research with me are Michael Spearpoint, Steve Gwynn and Anne Templeton. A bit of the background and motivation for this work. So while counterflow conditions are a common occurrence in some situations, for example in train stations or other transport hubs where you have opposing flows through corridors, doors, even stairs I suppose, it's not generally common in fire evacuations. However, there may be instances where some of the people that are moving against the predominant flow, such as emergency response personnel that are entering the building, and that begged the question for us that how should counterflow then be modelled in evacuation models? Some previous work, the kind of benchmark for some of this is in the ISO 20414, which provides a counterflow verification test in a corridor arrangement. So as shown on the screen here, we have two rooms that are connected by a 10-metre long corridor, and the test has varying levels of counterflow from 0 to 1, with 0 being unidirectional flow and 0.5 being an equal number of participants walking in opposing directions. In terms of some research work, Vara et al. Evaluated counterflows through the ISO 20414 corridor arrangement and compared FDS evac against versions of Simulex and the mass egress simulation tools. Additionally, Kretz et al. Present the results of counterflow experiments in a corridor. Interesting to note in this work was that for the scenario with 0.5 counterflow, where there's an equal number of participants opposing each other, the resulting flow was marginally greater than half of that in the corresponding scenario without counterflow. And lastly, Isobe et al. And Nagai et al. Modified a version of a lattice gas model to replicate the observations that were made in some experiments where pedestrians were walking and crawling along a corridor. Just that leads us on to the trials that we undertook in my company. So this was part of an author-initiated company team event where the company were gathered all together. So we saw the opportunity to get some data from this. There were between 88 to 91 participants with the sex demographic and age demographic shown on screen there. The number of participants varied as not everyone partook in every trial based on having to go and answer the phone or the like. As we were all from the same company, we were generally known to each other, which may have an impact on how the trials ended up. Onto the trial setup. So there was two rooms connected by a 1.72 metre door, as shown on the screen there. The door was formed of two leaves that were permanently held open, and touchscreen logging devices were used to measure the flow. So those are the four green squares shown there, where people would walk through and then just simply click on the screen, and that would note the time that they've passed through the door, essentially. A bit of a still image here, just showing the setup. So we have the two rooms, the interconnecting door, and you can see the logging station there with the green arrow just on a chair. Looking at the trials now, 8 trials were completed in total. The first 2 were with unidirectional flow. So that was where all 90 occupants just walked from one of the rooms into the other, and then vice versa. The next 2 were with what we've called random group counterflow. So this was where the population was separated into 2 groups of roughly equal size, and then would walk against each other. and the next 4 were with assigned group counterflow, which is we asked the participants to fill out a series of questions, and then we're told that they were put in a group based on that. So this was to investigate the effect of group identity, essentially. So yeah, participants were told that they were split into groups with distinguishing characteristics, whereas in reality these were again 2 random groups. Then for the in-group or assigned group trials, it was Christmas time, so the group identity aspect was reinforced by giving people green or red Santa hats, as we can see here in the image. And then the same trial was replicated where people would just walk against each other and log the times at which they passed through the door. Briefly then at the trial results, the results are shown here in box and whisker diagrams. First with the unidirectional flow with a mean of 1.67 persons per second, as shown on the left-hand side, and then the counterflow with no groups and counterflow with groups. The counterflow with groups had a slightly higher mean flow of 1.04 persons per second compared to 0.97 persons per second for without group. Interestingly, taking half of the measured unidirectional flow on the left-hand side would give a flow of 0.8 persons per second, which is 13 to 20% less than the measured counterflow in both no groups or groups. As you can see, the in-group can show an overall increase in flow rate compared to having random groups. However, the in-group counterflow also exhibits a greater variability during the stages of the flow should the participants interact, which in some trials, having reviewed the video recordings, we found to be the case. More in-depth results of the trials themselves are presented in the paper, so this was just a brief look at some of the headline results. Onto the modelling tools that we've looked at, so the first being the hydraulic model. This is described in chapter 59 in the handbook, the SFP handbook rather, and it describes the evacuating population using a set of equations. Using these and taking a specific flow of 1.3 persons per second per metre, as is given in the handbook for horizontal travel, and the door width, we get a calculated flow of 1.85 persons per second. And we could simply take half of this in a counterflow condition of 0.5 and take the counterflow as 0.92 persons per second. Next tool we looked at was Pathfinder. So Pathfinder, as some of you might be aware, has 2 simulation modes. In the first mode, steering mode, this is the default in Pathfinder, and agents use a steering system to move and interact with other agents in an attempt to emulate human behaviour. So the agents are assigned a space in the model such that they can interact or steer their way around other agents and the geometry. With this mode, you can assign personal distance limits to make agents stand closer together, or even now select social distancing to maintain a larger separation, which is quite interesting. The second mode is SFPE mode, which uses the same kind of hydraulic model as described previously, and hand calculations to work out the flow through constrictions. With this mode, agents make no attempt to avoid one another and can interpenetrate, which is where they'll just become superimposed in the same space within the model. And then the constrictions impose a flow limit and velocity as a function of the density in the space, and then discharge agents based on that flow. File arrangement was replicated in Pathfinder to compare the 2 simulations modes. First, we'll look at the results of the steering simulation. So I think we've got a little video here. Yeah, so here we can see the agents all go toward the exit. Those on the right-hand side told to exit on the left and vice versa. We can see that there's a congestion forms as the occupants or the agents bounce off one another. I think we've got a zoomed in image here. Yep. So the agents kind of bounce off one another and they eventually trickle through the opening and onto the exit, which on the face of it looks like a good representation of the trials. And yeah, eventually everyone gets through. So that's the steering mode. In the SFP mode, as agents can interpenetrate, they essentially group up on top of each other at the opening, at the constriction, with then agents kind of discharging based on the flow that's calculated on the density that's in the space. So we can see here that everyone just groups together and then eventually people are just discharged at the same rate. The last simulation tool we looked at is evacuations. This is a tool developed by one of my colleagues and co-author of this research, Mike Spearpoint. He's been developing the model over several years. As with the SFP mode in Pathfinder, evacuations adopts the same hydraulic model, imposing a flow limit and velocity through doors as a function of density. Again, with this model, agents can interpenetrate and they're not assigned a physical space in the geometry. For this work, the model has been updated to capture counterflow, whereby an equivalent half-door opening effective width is adopted as the first pass to compare the results of this simulation tool with the trials. Evacuations outputs into smoke view, so you can view the movement as you can with Pathfinder. And just an image here. This one looks very comparable to the SFP results, where the agents just group round the constriction and are just discharged at a given flow rate. I think this one's slightly sped up in comparison. That's why it looks a bit quicker. But yeah, the times are comparable. Onto the results of this. Firstly, looking at the unidirectional trials and compare these with the evacuation models. So the two unidirectional trials shown here are largely consistent in terms of the flow rate, with trial 1 being the first one. There was a little bit of confusion in terms of what to do, so that's why that was a slightly longer, but yeah, largely consistent. Then, as one might expect, the results from the three evacuation models closely aligned to the trials, more so to trial 8, as mentioned, because trial 1 was slightly protracted there. So we can see the three dashed lines all follow the same trend and land at around the same time for everyone to pass through the door. And just looking at numbers, so you see there's a bit of a difference there between trials 1 and 8, and then the four results for the models are all around the same ballpark. Some being a bit quicker, some being a bit slower. To look at the counterflow results now, we'll first look at the random group counterflow, where people were just split without the hats, essentially. In this trial, it's trial 2 we're looking at, the groups were not evenly split, which was corrected for subsequent trials. But you can see here that the number of people was about 38 versus about 60, which, yeah, it had the unintended benefit, this actually, of assessing how the evacuation models would respond to a scenario where the counterflow condition ceases and essentially turns back into unidirectional flow. So here we can see the results of evacuations in the SFP mode in Pathfinder. We can see the gradient of the model curves increase when the counterflow ceases. You can see the inflection on the two orange dashed lines. This wasn't observed in the trials, but it does make sense from a theoretical perspective, as the effective width the occupants have to pass through the constriction has increased. This wasn't observed in the trials. We reviewed the results of the videos and showed that participants didn't utilise this additional width. Rather, they remained in the queue that had already formed over the previous 40-50 seconds and just kind of followed that same passage, really, without increasing the overall flow, which was quite interesting. The next takeaway here, if we look at the steering mode in Pathfinder, we see significantly protracted flow through the door of those two new lines that kind of tail off to the right hand side. Again, we do see the same inflection on the brown line. But yeah, so from reviewing the visualization visualization results within Pathfinder, the agents can be seen colliding with one another and taking a significant period of time to negotiate the collision, which results in the door becoming blocked essentially for small periods of time until that collision can be negotiated. This wasn't observed in the trials typically, as participants generally formed lanes, as we said previously, to pass through the door, and where participants did actively cut across the face of the flow, the collision was resolved quickly and the flow continued. Onto the in-group counterflow trials. As I said, the group sizes were amended to result in a similar number of participants travelling in each direction. I believe in this case it was 46 versus 48 people, so almost equal. We can see the results from here. Those in the red hats kind of moved a little bit quicker, with the green hats being a bit slower to start off and then getting through the constriction a bit quicker toward the end. Again, we'll compare the results firstly to the evacuations and the SFP modes in Pathfinder, which show kind of comparable results themselves, and then also comparable to the trial results, albeit marginally conservative, with the flows being slightly slower overall. While agent interaction or kind of the in-group identity dynamic could be implicitly represented within the computer models, for example, by altering some relevant parameters, we decided not to incorporate this due to a lack of data to support any changes in the value of these parameters, and rather just kept the same simulation as was. Again, when we look at the steering mode in Pathfinder, we see that protracted result with a counterflow rate that is of the order of half of that of the other simulations and the trial counterflow rates. So again, it's just a similar result there. Looking at the results in some numbers, we see that the in-group trial average slightly increases over the random group trial average. In the hydraulic model, which we just took as half of that of the calculated unidirectional flow, it's kind of in the same range. And then the three modelling results shown there. So 5 of the 6 of these yield comparative results for the counterflow rate ranging from 0.9 to 1.05 persons per second. But then there is that one outlier that we discussed there previously. Slightly more discussion on this. We did consider select variables that may affect the counterflow rate in steering mode. So there's 2 that were considered to affect this. The first being the ability of agents to reduce their diameter to resolve congestion. For this parameter, the default in Pathfinder is 0.7. And it's considered a means to get the benefit of an elliptical agent shape corresponding to someone that would turn 90 degrees and essentially turn sideways to squeeze by one another in congested areas. This parameter was reduced to 0.5 to assess its impact, with the results showing an increase of 11% in the counterflow rate in the steering mode. The next parameter is the agent's personal space factor. The default here in Pathfinder is 0.08 meters, and we decreased this to 0.05 and showed that it had a kind of negligible impact on our results. I think it was around 0.2% increase in flow. So while there is a possibility to alter these parameters, we thought care should be taken really with any sort of justification for these, and would probably err on the side of sticking with the defaults as being more representative in lieu of further research. On to the conclusions. It's worth noting that the trials that we undertook were limited in number and scope. However, the following conclusions are drawn. So a representative effective width for the counterflow. Applying the hydraulic model to counterflow suggestion would suggest that using a half door width as evacuations does provides marginally conservative results. Flow rates through the doorways around 13 to 20% greater in the trials than assuming the half effective width, so we are on the conservative side there. Agent interaction in the models that might work in unidirectional flow can introduce challenges in counterflow. So by that we mean the steering mode in Pathfinder underpredicts the counterflow rate. While visually it may look better in terms of the visual output, Compared to the Pathfinder SFP mode and evacuation models, these more closely align to the results we observed in the trials. And lastly, the group mentality dynamic. It was shown that the flow increased marginally when the in-group psychological behaviour is introduced. However, again, noting that the trials are limited in number and scope. That's all for me, so thanks for listening, and if you have any questions, I'm happy to take these now, or if you want to catch me after the talk today, then that's fine with me. Thank you.
Okay, so Matt's unavailable for live chat right now, so if you could please put your questions to him in the Q&A, and we'll make sure he sees those. It might be helpful just to mention his name in the question at the top, like Matt, how do you, et cetera. So with that, I think we'll go to the next speaker.